Okay, let's start chapter 7, reaction rates and equilibrium. When you're doing a chemical reaction, it's important to know how much product I'm going to get. Generally, what we're looking for is we're looking for 100% product if we can possibly get it. But it's also important to know how fast a reaction occurs. And those two things are not necessarily linked. I can have a reaction that gives me 100% product, but happens very, very slowly. Or I could have a reaction that happens very quickly and gives me very little product. A great example of that would be diamond and graphite. Diamond and graphite are both carbon. It's just the atoms are hooked together differently. We talked about that back in chapter 5. Well, one of these is more stable at room temperature and room pressure. And I will give you a hint, it's the one you see more of, and it would be graphite. Graphite is the stable form of carbon at 1 atmosphere, 25 degrees Celsius. Diamonds are formed under extremely high pressure and extremely high temperature. Well, it turns out there's actually a reaction here, an equilibrium reaction, where diamond converts itself into graphite. So if you have a diamond ring, that diamond ring is actually converting itself back into graphite even as we speak. The good news is that particular process is really, really slow. And so it would take hundreds of thousands of years for your diamond to turn into graphite. You're going to be dead and gone. Your relatives are going to be dead and gone. You're not going to care by that point. So this is a great example of a reaction that gives me a lot of product, but it takes a really long time to get there. And it's important to know how much am I going to get, but it's also important to know how fast am I going to get it. If I have a reaction that gives me 100%, but it takes 10,000 years, it might as well just give me 0%. How fast a reaction occurs is something called chemical kinetics. How much product I'm going to get is thermodynamics. These two things are separate phenomena, and you have to measure them actually separately. If you know something about the chemical kinetics of a reaction, you know absolutely nothing about the thermodynamics. If you know something about the thermodynamics, that tells you nothing about the kinetics. So what we're going to do in this chapter is we're going to start out and we're going to talk about chemical kinetics, and then we're going to talk about thermodynamics. So let's talk about kinetics and reaction rate. Kinetics tells me how fast a chemical reaction occurs. All right. The reaction rate is governed by a rate constant, little k. All right. Some reactions occur fast, some reactions occur slow. Why? Well, zinc reacts with hydrochloric acid really quickly and copper doesn't because zinc is zinc and copper is copper. So each particular chemical reaction has its own rate constant, K. And if I have a large value for K, little k, that's a very fast reaction. If I have a small value for little k, that's a very slow reaction. So the other thing that the reaction rate depends on, it depends on the concentration of the reactants. Hydrochloric acid will burn you faster than dilute hydrochloric acid. So I can take those two things and I can put those together into an equation that looks like this. The reaction rate, in other words, how fast a reaction occurs, is equal to K, the rate constant for the reaction, times the concentration of the reactants. So from this equation, you can see if K is large, reaction rate is very high. If the concentration of my reactants is very high, that also makes my reaction rate high. All right, well, there are three requirements for a reaction to take place. The first requirement is the reactants must touch or collide. If I have a beaker of hydrochloric acid over here in one corner and a piece of zinc in the back of the room, they're not going to react. I have to put the zinc in the hydrochloric acid. So for those two things to react, they've got to touch. If they don't touch, they're not going to react. But it turns out that not every collision causes a reaction. All right, so it's kind of like, in kind of a morbid example here, but it's kind of like car wrecks. Not every car wreck results in a fatality, right? All right, so what would make you more likely to die in a car accident? Well, the first thing in a chemical reaction is your reactants must collide in the proper orientation. So, say for example, we're talking about our car wrecks. Someone runs into you from behind or something like that. It's probably going to mess up your car a little. Odds are it's probably not going to kill you. The bad ones are when you collide head on or somebody T-bones you, running through a stoplight or something like that. Much more likely to cause a lot of damage that way than if somebody just runs into your trunk or something like that. Well, it's kind of the same way in a chemical reaction. If I have two molecules, and let's say the front end of this molecule is going to react with the front end of that molecule, they have to collide, but they also have to collide front end to front end for the reaction to take place. If they collide front end to side or front end to back end, then they'll just bounce right off each other and you'll have no chemical reaction. The larger the molecule, the less likely they are to collide in the proper orientation. And so this is sometimes called your steric factor. It's given by rho, Greek letter rho. Basically, the bigger the molecule, the smaller the likelihood they are to collide in the proper orientation. Right? This is how enzymes work in your body. Enzymes speed up chemical reactions in your body, 1,000 to 100,000 times faster than they would happen just on random. And the way most of them work is they will grab hold of a certain molecule and they will hold it in a certain orientation so something else can come in here and hit it and react. And so you get more effective collisions that way. Enzymes are kind of the assembly line workers in your body. They do one thing, and that's it. Usually, when you see ACE on the end of something in biochemistry, that's an enzyme. If you see ose on the end of something, that's usually some sort of a carbohydrate or sugar. So lactase, the enzyme lactase, is responsible for breaking down the sugar lactose, which is what you find in milk. All right, and that's all lactase does. It just works on lactose, doesn't work on anything else. It's a specialist because lactose has a certain shape and that enzyme fits around that particular shape just perfectly, and then it holds it in a certain orientation, and so I get a reaction. If you waited for the food you eat and the molecules that have to work on it, if you waited for that to happen by random chance, you'd be dead because you have a certain amount of time you've got to get the energy from that food. And so enzymes speed things up. These are biological catalysts here, and they're very specialized molecules. So it's not the number of collisions that I have, it's the number of collisions that collide in the proper orientation. Well, it's not even those. It's the fraction of those that collide with a certain minimum energy. Back to our example of car accidents here. Let's say, for example, someone runs into you at 10 miles per hour. Let's say someone runs into you at 60 miles per hour. Where are you more likely to get seriously injured? In a car wreck at 10 miles per hour or in a car wreck at 60 miles per hour? Well, a 60 mile per hour car wreck, right? Are you exactly 6 times as likely to get seriously injured in a 60 mile per hour wreck than a 10 mile per hour wreck? Well, no, I would probably assume that you would be much more than 6 times more likely to get injured in the 60 mile per hour car wreck, even though you're only going 6 times faster. Why? Well, because there's just not enough energy in a collision at 10 miles per hour. Someone bumps into you at 10 miles per hour, you might spill your tea that you're drinking there, or your Coke, but that's probably about it. A 10 mile per hour car wreck's not going to kill you, and it's not going to break bones. But someone slams into you at 60 miles per hour head on. I hope you're wearing your seatbelt because that's a lot of energy there, and you're much more likely to get seriously injured there. Well, it's kind of the same way with chemical reactants. When my reactants come together, if they're coming together too slow, what happens is the repulsive force of those electrons around them kind of push them away again. And so they come together and then they just kind of go back off. And so I have a collision there that is not effective. But if I slam them together somehow with high energy, I overcome those repulsive forces from the electrons. The electrons come together and then they start to bond with each other, and I start forming chemical bonds. All right. So it's not the total number of collisions that make a reaction effective. It's the fraction of those collisions that collide in the proper orientation. And then it's the fraction of those collisions that will collide with that certain minimum of energy. And if I satisfy all three of those things, then I have an effective chemical reaction. Well, the amount of energy that it takes, that certain minimum energy to get that reaction started, is something called the activation energy. All right. A great example of that would be your Bunsen burner in lab, for example. You go into the lab, you turn on your Bunsen burner, up pops a little flame, and it burns all hour, right? Well, no. If you turn the gas on, you'll just get a lot of gas in the room. So, what do you have to do to get your Bunsen burner lit? Well, you have to provide a certain minimum energy in the form of a match or a striker to get the reaction going. Once my natural gas starts reacting with oxygen and starts burning, do I have to keep adding? Do I have to keep the match in the flame? No, I can take the match out, it will burn on its own. But if I don't provide that little bit of energy to get the reaction started, nothing happens. Well, that's activation energy. All right. So, for example, this is called an energy profile diagram. So, on this axis here, this is energy, and this is what we call our reaction coordinate. It's basically time. As time goes on, my reaction progresses closer to 100%. So, here are my reactants here. Here are my products. Why do things react? Well, things react because my reactants are higher in energy than my products. All things being equal, atoms and molecules prefer to be in the lowest energy state. So if I can somehow go from here down to here, that's a good thing. All right. So you can think of it as kind of like a ball. If I take a ball and I put it at the top of the hill and I give it a little push, will the ball roll down the hill on its own? Sure, it will. All right. If I take a ball at the bottom of the hill and give it a tiny push, will it roll up the hill on its own? No, it won't. Okay. So reactions that happen on their own are what we call spontaneous reactions. Like, for example, that natural gas reacting with the oxygen and in your Bunsen burner. Okay. And it's kind of like a ball that rolls down the hill. Reactions that don't happen on their own, we call those non-spontaneous reactions. And that's kind of like dropping a ball and having it roll up the hill somehow. All right. So let's say, for example, I've got a little ball that's sitting right here. We're trying to go down to here, and we say balls roll downhill, right? So if I give that ball just the tiniest of pushes, will it roll down the hill on its own? Well, no, it won't. Why? Well, because what I've got to do is I've got to go up this hill first. All right. Well, let's say, for example, I gave the ball just enough energy to go up this hill and get to right here. Once I get to right here, do I have to keep pushing the ball? Well, no, then the ball will just kind of roll down the hill on its own, right? Okay. Well, that energy that you have to add just to get to the top of the hill, that's called the activation energy, or E sub A here. In this case, it's this amount of energy right here. And that's the minimum energy you have to add to get a reaction started. All right. So it's kind of like running a business. If you want to run a business, you can't just open a business and start making money. You have to put a certain amount of money into it to begin with to start making a profit. So say you want to build a hamburger place, or say you want to sell clothes. All right, well, you got to find a store somewhere, and that's gonna cost you rent, and you got to advertise. You got to buy all the clothes, and you've got to hire some workers, and so you're going to be outlaying a significant amount of money. Well, after your first year, you're probably going to lose money. That's the way it is in business. Your first year, you usually lose money. By the second year, though, you don't have to buy those things anymore. You're still buying clothes, but you've got some inventory. You're not having to redecorate the building or anything like that. And so now, maybe if you're lucky, the second year you break even. And hopefully by the third year, now you start making a profit. But if you hadn't put that money in there initially invested, you wouldn't have a business at all. Well, it's kind of like your activation energy. So here I've got to add this much energy to get the reaction started. But once I get the reaction started, it's going to go on its own. All right. Here's another one over here. Here's my reactants. Here's my products. Okay. In this case, I have to add energy to get to the top of the hill, but I don't have to add as much energy, say, before the ball rolls down the hill. So this is an example of a reaction with a low activation energy. This is an example of a reaction with a high activation energy. All right. The activation energy tells me how quickly a reaction will go. So let's say, for example, this little situation over here is like, let's say you want to sell clothes, but you really don't want to build a store. You want to get on eBay and do it. You want to do an eBay business there. So what do you need to get on eBay? Well, you got to have an email address. You got to have a computer. Can you set that up pretty quick? Sure. Do you have to spend a lot of money? No. You don't even have to have the clothes. You could have them drop shipped maybe from the manufacturer, and you could not even have a warehouse, to own an eBay business. And so that's why there are a lot of businesses on eBay because you can set things up really quickly and get going without investing a lot of capital outlay. Well, this reaction is a reaction with low activation energy. This one is high. Which one of these reactions do you think would be faster? Well, this reaction over here with a low activation energy. Because see, I don't have to build up as much energy to get to the top of the hill before I get going. So there's a correlation here between the activation energy of a reaction and its speed. All right. High activation energy means slow reaction. Low activation energy here means fast reaction. The top of the hill here is something called the transition state. The transition state is the highest energy state between your reactants and products. Transition states are species that my reactants go through on their way to products. The ball doesn't go to the top of the hill and stop and then go down. As the ball comes over the hill, I could take a picture of it here, but it never really stops there. It just kind of goes up and over. Well, that's what a transition state is. My reactants go from here through a transition state, but then I end up down here in products. All right. So the activation energy is the energy it takes to get from your reactants up to the transition state, basically. High activation energy, slow reaction. Low activation energy, fast reaction. Well, here are 4 factors that affect reaction rates. These are things that I can change to make a reaction go faster or slower. Sometimes I want a reaction to go slower. If I have a reaction that's going too fast, what do we call that? Well, we call that an explosion. We don't want those. So sometimes we want to slow reactions down, if we possibly can. So what are the 4 factors? Well, the first one is kind of the trivial one. It's the nature of the reactants. As I said before, zinc reacts with hydrochloric acid really quickly. Copper reacts very slowly. Gold reacts pretty much not at all. Why? Well, because zinc is zinc and copper and gold is gold. That's just the way it is. There's probably not much you can do to change that. Some things react fast, some things react slow. All right, so not much you can do about that one. The others, though, you can do something about. The first thing is concentration. All right, and the way this works is the higher the concentration of my reactants, the faster the reaction. Remember our little equation up here where reaction rate depends on K times the concentration of the reactants. So mathematically, we can see how if this number is bigger, that makes this reaction rate higher. All right, so which will burn you faster, concentrated hydrochloric acid or dilute hydrochloric acid? Well, concentrated hydrochloric acid would burn you faster because it's higher concentration. So if I have a reaction that's going too slow and I want to speed it up, I just use more concentrated reactants. I use 6 molar sodium hydroxide instead of 1 molar sodium hydroxide. If I want to slow it down, I use more dilute reactants. Maybe I use 0.5 molar sulfuric acid instead of 6 molar sulfuric acid. All right, the third factor that affects reaction rates is the temperature. And the way this works is the higher the temperature, the faster the reaction. So why is that? Well, if I raise the temperature, what that's going to do is that's going to give the molecules more energy. And so therefore, the more energy they have, the more collisions I have. And so therefore, the faster the reaction. Now, you would think if I doubled the temperature, well, that would double the reaction rate. But that's actually not true. General rule of thumb over here for most reactions, works for most reactions. For every 10-degree rise in temperature, your reaction rate doubles. So if I go from, say, 25 degrees to 35 degrees, and I do the same reaction, it will happen twice as fast. If I go from 25 degrees to 45 degrees, well, when I go from 25 to 35, it doubles. When I go from 35 to 45, it doubles again. And so from 25 to 45, it will actually happen 5 times faster, or excuse me, 4 times faster, 2 times 2. All right. Well, if I go from 20 degrees to 30 degrees, I haven't doubled the temperature. I mean, remember in Kelvin, that would be 293 to 303 Kelvin. So I haven't doubled the number of collisions. Why do I double the reaction rate? Well, remember, it's not the number of collisions I have, it's the number of effective collisions I have. By giving a 10-degree rise, what you've done is you've doubled the number of molecules that have that minimum energy to collide and provide an effective collision. All right, so you're not doubling the number of collisions, you're doubling the number of effective collisions. And that's a pretty good general rule of thumb for most reactions. Ethers, for example, ethers, if you let them sit on the shelf over a long period of time, will form peroxides, organic peroxides, which can actually be explosive. So usually you try to use up your ethers, and you don't order big giant 55-gallon drums of it unless you need 55 gallons of it. What we do is we actually keep our ethers in the refrigerator. They're in a bottle with a sealed septum, which keeps the oxygen out of there, which keeps the ether from forming the peroxides. But we put them in the refrigerator because if for every 10-degree rise in temperature your reaction rate doubles, then that means for every 10-degree drop in temperature, your reaction rate does what? Well, it goes down by half. See? And so by putting it in the refrigerator, those peroxides will form much more slower, and our ether stays good longer. So yeah, sometimes you want to speed reactions up, but there are certain reactions you actually want to slow down. But if I'm sitting there in lab and it's about 3:30 and I really want to get out of there, maybe I heat some things up. Maybe that starts things moving a little faster. Okay, the fourth thing here is the presence of a catalyst. So what is a catalyst? Well, a catalyst makes a reaction occur faster. Well, a reactant, if I double the concentration of the reactants, that makes it occur faster too. So what's the difference between a reactant and a catalyst? Well, a reactant is actually used up in the chemical reaction. If I add 2 moles of chemical A and there's none left, or there's half a mole left, or something like that, by the end, it's a reactant. A catalyst is not used up in the reaction. So if I start with 4 grams of a catalyst, and at the end of the reaction, I end up with 4 grams of catalyst, that makes that a catalyst and not a reactant. So if my catalyst isn't used up, how does it make the reaction occur faster? Well, catalysts make a reaction occur faster by providing a pathway of lower activation energy. So here is our little energy profile diagram again. Here's our reactants, here's our products. This is my reaction here without the catalyst. All right, so here's my activation energy. It's the energy between the reactants and this transition state up here, the height of the hill, so to speak. All right, well, what a catalyst will do is it will provide an alternative pathway of lower activation energy. So instead of going straight over the mountain, it's like finding a mountain pass and kind of going through there. All right. Notice that this is my alternative pathway. My activation energy for this reaction with the catalyst is only this much. Now, which one of these would occur faster? This one, the solid line, or the dotted line? Well, the dotted line one, because it has a lower activation energy. And that's how catalysts speed reactions up, is they provide an alternative pathway there of lower activation energy. All right. And there are multiple ways they can do that. They can provide a substrate for my chemicals to stick on and hold them in the proper orientation. Some catalysts will go through what we call a catalytic cycle. In other words, they'll react with my reactants and make that thing more reactive so my product can come in and react with it, and then they'll leave. So it starts in the reaction, and then at the very end, it gets kicked off. It's called a catalytic cycle. Some of them work that way. But it doesn't matter how they work, is if they lower that activation energy and I still have my catalyst at the end that I started with, that's what makes a catalyst. All right? Okay, and those are 4 things I can do to speed a reaction up. All right, well, that takes care of how fast. How much product am I going to get? Well, everything that we've talked about so far tells me absolutely nothing about how much product I'm going to get. All that tells me is how quickly it occurs. I could get 20% product, I could get 100% product. All the reaction rate tells me is it fast or is it slow? What tells me how much is the thermodynamic factor, okay, and something called equilibrium. All right, so let's talk about that. To really understand this, you need to know something called static versus dynamic equilibrium. So we'll talk about this. We'll probably end it here, and we'll talk about this in more detail in the next video. So let's say, for example, I've got a chemical reaction here. 2HI goes to H2NI2. All right. This little double arrow here means equilibrium. All right. Last chapter we talked about it. We said it means partial. We talk about it later. We're going to talk about it right now. All right. So here is, let's say I've got a bucket here and it's holding water. Okay. And I want that bucket to be half full. So how do I get my bucket half full? Well, I turn on the garden hose and I fill it up half full and I turn the garden hose off. Right? Okay. So I got a certain number of water molecules in the bucket here. If I leave and come back 10 minutes later, will there still be the same amount of water in the bucket? Well, discounting evaporation. Sure. Are the water molecules in the bucket the same 10 minutes from now as they will be now? Yes. All right. Well, let's say I've got another bucket over here, but this bucket has a hole in it. Okay. Is there any way I can keep this bucket half full of water? Well, it's possible if I leave my garden hose on. And if I add water into the bucket at exactly the same rate as the water is leaking out, my level will stay exactly half full. So let's say, for example, I leave the hose on and I go away for 10 minutes and I come back. Is the bucket still half full? Yeah, the bucket's still half full. Are the water molecules in the bucket 10 minutes from now going to be the same ones from now? No, because I've constantly got water leaving, but I've got water replacing it. And as long as the water is leaving at the same rate as the water is coming in, my level is going to be the same. Well, this is what we call a dynamic equilibrium. Okay, this situation over here is what we call a static equilibrium. A static equilibrium is where everything kind of comes to a certain point and it just kind of stops. And so the concentration here, or in this case, the level of the water, is the same because, well, nothing's happening. But in a dynamic equilibrium, things are still happening. Okay, they're just happening at equal rates. So it's like running on a treadmill. You can run and run and run on a treadmill and not get anywhere. Why? Well, because you're running this way and the treadmill's going back this way. And as long as you're running this way exactly as fast as the treadmill's going that way, you're going to end up right in the same spot. What if you decided, I don't want to run anymore? What's going to happen? Well, you're going to fly off the back of the treadmill, right? Okay. Well, chemical equilibrium is a dynamic equilibrium. So when we have a chemical reaction such as this, what's really happening is at a given point in time, I will have HI here decomposing into H2 and I2. At the same time, I have H2 and I2 coming together to make HI. So I actually have two reactions going on at once. When I reach a point at which the HI is decomposing just as fast as the H2 and the I2 are forming HI, then the concentrations of all these species stays the same. And it looks like nothing is happening. But something is still happening. The rate of my forward reaction is now equal to the rate of the reverse reaction. The concentrations are constant, and we say that my reaction is in equilibrium. And it's kind of like this situation over here. The water level doesn't change, but there's still stuff going on. So when we say that a reaction goes to equilibrium and the concentrations are constant, you need to kind of in the back of your head realize they don't go to that certain concentration and then everything stops. There's still stuff going on. It's just that the rate of the forward reaction is now equal to the rate of the reverse reaction. And that's really what this double arrow means. All right. So, what does that have to do with chemistry? And is there any way I can predict how much product am I going to get knowing something about this equilibrium? Well, yes, there is. And I guess that's what we'll talk about in the next video. So in the next video, we'll talk about another constant, the equilibrium constant, big K, instead of little k. Why they gave them both Ks, I don't know. Just seems like a confusing thing to do, but that's where we are. So we'll talk about the equilibrium constant K, and we'll move on from there. So I guess we'll see you in video 2. So bye for now.